Hello friends and welcome to the fifth part of this video tutorial series on molecular dynamics. In previous video we have seen how to simulate this LJ potential, and we have also discussed some methods using which we can speed up our algorithm, right? In this part we are going to talk about this Lorentz force, and lastly we will summarize our presentation. So without wasting time, let's start now. So the theory for Lorentz force is this. For a system of n particles, the Lorentz force acting on the ith particle is given by this formula. Here this capital Qi is the charge on ith particle, this Ei is the electric field on ith particle, and this Vi is the velocity of ith particle, right? Here the expression of electric field is this, right? And this Ri is the distance from the origin. And as we are using normalized unit, we will assume that this constant is 1, right? Now as we are dealing with magnetic field, we must know that magnetic field doesn't contribute in potential energy, right? So potential energy due to this V cross B term is 0. So only electric field will contribute to our potential energy, and we already know that this for a system of charged particle, potential energy is given by this expression. We have covered this thing in a video on Coulomb force, right? So now let's understand this type of system with some examples. The first example says that consider a system of two oppositely charged particles placed on x-axis. As you can see here, their velocities are as depicted in this figure. Okay, so they are pointing to each other, and we want to study the motion of such system, and also want to plot kinetic energy, potential energy, and total energy of this kind of system, right? Now before we jump to this simulation part, I want to know from you guys that what will happen in normal scenario. What will happen is, as these two are oppositely charged particles, they will just stick to each other due to attractive force, right? But in this case we have magnetic field, right? So let's see what will happen. Okay, so let's jump on this simulation stuff. See, as our problem say that we want to simulate two particles, so I'm writing in this input.txt file that n is equal to 2, right? And I want to simulate this thing for 12 units of normalized time, right? And dt is 10 raised to minus 3. This dt is the accuracy, okay? And this b is the magnetic field, okay? And as we have done in previous parts also, in this part also we will first initialize our parameters. Okay, so these are the coordinates of our particle. As you can see, they are placed on x-axis, -2 and 2. Okay, these are the x coordinate and this are the y coordinates. These are the velocities. As you can see here, they are pointing towards each other. This is the mass and this is the charge. As you can see here, we have oppositely charged particle. This one is for negative charge and this one is for positive charge, right? Now let's run this code and initialize our parameters. So yes, we have initialized our parameters. Now we will run this main.py file, right? And we have already discussed this Boris algorithm, as I have mentioned in previous presentation, that in the presence of magnetic field we will use Boris algorithm, right? So as you can see here, let me maximize this window so that you can see here. So with this function I'm calculating my electric field. As you can see in this so this expression, with this expression I'm writing this function to find out the electric field on ith particle, right? And this is my Boris scheme. As you can see here, this Boris function will calculate the coordinates of my particle at tth time, right? So here also I am first finding the half velocity. This is the initialization part of this Boris algorithm, guys. Next is my actual Boris algorithm. Okay, so as we are dealing with a two-dimensional world, many complicated equation became very easy, right? So this is my Boris scheme, okay? And yes, after running this code, we will have coordinates at teeth time, right? So let's run this thing and see what we are getting. Okay, so yes, process is completed. Now we want to plot this data, okay? So I will run this plot data.py file, okay? So let's run this thing and let's see what we are getting, which kind of yes, this is the energy profile, guys. So as you can see here, we have this orange curve, which is our kinetic energy, and this green curve is our potential energy, right? And here also our energy, total energy, is remaining constant. That means this simulation is correct. Okay, this is the we must check this thing. Let's try to animate our simulation, and let's first keep 100 data points to speed up our animation. Okay, so due to attractive force, they are coming close to each other, but as they are coming closer to each other, magnetic field comes into the picture, right? And that V cross B term starts to dominate, and we have this kind of a profile. As you can see, they are coming closer to each other, and due to magnetic force, or say magnetic field, they are moving in a kind of a circle, right? And this kind of energy profile we have, right? Let's shift our focus to result and discussion. So as we can see here, we have two oppositely charged particle, right? And we have also noticed here that this particle don't stick to each other due to the magnetic force. So what is happening, guys, here? Initially, electric force dominates, and due to that electric force, they come closer to each other. But in that scene, means in when they are coming closer to each other, their velocity is increasing. As you can see here, initially their kinetic energy is increasing, right? And this increase in kinetic energy give a rise to a magnetic force. That V cross B, this V cross B term comes into the picture as velocity is becoming higher and higher in magnitude. Okay, so that's how this magnetic force comes into the picture, right? And that give rise to this turning effect. Now we have second example. In this example, we have two like charged particles. So this example says that consider a system of two like charges placed on x-axis. As you can see here, their velocities are as depicted in this figure. Same, okay, they are pointing towards each other. Study the motion of such system and also plot the kinetic energy and potential energy, and also plot total energy of this system. Now as we know that these are the like charges, so due to the repulsive force, what will happen? They will just fly away. Initially they will come closer to each other because this due to this velocity, right? But thereafter they will just fly away, as we have seen in Coulomb potential. But in this case we have a magnetic field. So let's see what kind of effect we are getting in this example, right? So let's jump to our input parts. Sorry. And we want to simulate two particles. We want to simulate this system for 12 seconds of normalized time, and dt is going to same, and magnetic field is also 1. Now let's initialize our problem for the second case. This experiment 2 is the input for second example, right? So all things are same, okay, and in this case we have like charges, right? So we have 1 and 1 means they have positive charge, right? So let's initialize our problem by running this code, and now we will run this main.py to find out the answer, or say to find out the coordinates for this system. Okay, and lastly plot data.py. Okay, so we are getting this kind of interesting energy profile, guys. We have this orange kinetic energy and green potential energy, right? And luckily in this case also we have constant total energy. That means our simulation is correct. Let's run this thing. or let's simulate this. Okay, so we are getting this kind of energy profile. They are kind of moving in a circle, right? Okay, so they are coming closer to each other. Okay, so the same thing here also, as the velocity term comes into the picture, we have kind of a turning effect due to that v cross b term, right? And due to that v cross b term, this system is remaining in a bounded state, right? They are not just flying away, okay, due to that term. So let's jump to result and discussion. Okay, so we have noticed that these two particles don't fly away due to the magnetic force. Electric field try to repel this particle due to that charges, but this magnetic force tries to bound this system. Okay, so this we have noticed in this system. Now let's discuss some tough example, the third example, right? So this example says that consider a system of 4 like charge particles. Their initial positions are as depicted in this figure, as you can see here. And this system doesn't have any initial kinetic energy. Okay, study the motion of such system and also plot kinetic energy, potential energy and total energy of this system. Now this kind of example we have already seen in Coulomb potential, right? And in that part we have seen that they are just they just fly away due to repulsive force. Okay, and in that manner also this example is very interesting, as you will see direct effect of this magnetic field. Okay, so let's simulate this system. We want to simulate 4 particles, so I will write n is equal to 4, and I will run this simulation for 10 seconds of normalized time. dt is going to same, and b magnetic field is also going to be same. Now let's initialize our problem. Okay, so these are the inputs for third experiment. By the way, I will upload this codes on my GitHub account, so no need to worry about the code. Okay, just focus on the physics behind this problem. Okay, so as you can see here, these are the coordinates, and as you can notice here, we have 0 initial velocity, and these are the masses, and these are the charges on each particle. Now let's run this thing and initialize our problem, and now I will run main.py file to find out the answer for this problem. Lastly, I want to find the plot or say energy profile of the system, so I'm running this thing. Okay, so we are getting this kind of energy profile. Okay, so here also our energy is remaining constant, so that's a good news. Now we will run this simulation to see what kind of pattern we are getting. So let's run this thing. Okay, so yes, initially they are okay. Now they are moving in a circular manner. Okay, yes. So here in this peak we have seen that repulsive force dominates, right? So as they come closer to each other, this repulsive force starts to dominate, and when they sorry, and they are let's say far away from each other, okay, then this magnetic force tries to dominate on this system. Okay, let's run this. Let's see results for this thing. So we have noticed in this example that these particles don't fly away due to the magnetic force. This is the complete opposite behavior from what we have seen in this Coulomb potential, right? Here you can clearly see the what we can say the effect of magnetic force. Okay, so this what we have learned in this problem, guys. Now comes the fourth problem. This problem is very much similar to this third example. So this problem says that consider a system of four like charged particles, as we have seen in third example. These particles are in the presence of strong magnetic field. Okay, so this magnetic field is going to be much stronger. Their initial position and velocities are as depicted in this image, and we want to study the motion of such system by plotting all kind of energy. And with this example, we will see how this magnetic force tries to what we can say bound system very strongly, as magnetic field is very strong. Okay, so I will jump to this inputs.py, and is going to be same, but simulation time is going to be 5. Okay, and as I said, we want very strong magnetic field, so we are increasing this B by factor of 5. So 5 times stronger magnetic force, right? Let's initialize our parameters. Yes, we have okay, we have initialized this thing, and now we will run main.py, and lastly I will run this plot.data.py file. Okay, so we are getting this kind of energy profile. As you can see that there is a very much low interaction between kinetic energy and potential energy. Okay, and let's see what kind of animation we are getting. Let's run this do my work code. As you can see here, they are hardly moving, and this kinetic energy is remaining almost 0, right? So this is due to our magnetic field. Due to this magnetic force, these particles hardly move, right? And let's shift our focus to this presentation. So we have noticed that this particle hardly moves due to this strong magnetic field. In this weaker magnetic field, we have higher interaction rate between kinetic energy and potential energy. But in the case of strong magnetic field, this interaction reduces drastically. So this ends our fourth example. And guys, I have also mentioned in my previous videos that I have worked on this Boris algorithm, and this is something what my final year project look like. As you can see here, I have simulated 9 charged particles, right? And I have also plotted the Larmor circle associated to this particle. So what is this Larmor circle, right? So what happens is, guys, that in the case of Lorentz force, we have something called Larmor radius, and from that Larmor radius you can plot this kind of a circle. So that thing which I have done in my project, and here I have also plotted this energy profile to check whether my simulation is correct or not. And I have also plotted this velocity distribution for this system. Now there is no meaning to plot this velocity distribution, as I have only 9 particles, right? But if someone has, let's say, 100 particles, or say millions of particles, then this velocity distribution plot becomes very informative, right? So what you can do is, if you have a very high number of particles, let us say 10,000 particles, so what will happen, you will have a kind of a distribution of velocity, and in that case you can fit a Maxwell curve in this distribution and find out the temperature associated to this system. So this kind of a cool thing you can do with this molecular dynamics and this multi-particle system, okay, and study the physics behind this system. Okay, so now let's summarize our presentation. Okay, in this final part, it is safe to say that with the help of an excellent strategy, we have developed codes to simulate multi-particle system. in different potential like Coulomb potential, gravitational potential, LJ potential, right? And lastly, in this video we have seen magnetic force also. Next is, by taking different examples, we have studied the dynamics of various systems and also plotted energy profile of that system. Okay, and we have extracted uh, physics from that examples, right? And lastly, we have also seen some comments on how to speed up our algorithm. As I said in previous video, where we have discussed this third pillar, speed pillar, that in a real scenario we may have 10,000 particles or say millions of particles, and in that case our Python script will not work. So we have seen how to speed up our algorithm. So that's it for today, guys. This also ends our presentation on multi-particle system. See you guys in the next video. Bye.